In a moment of silence, when we look up at the night sky, have you ever wondered, could someone be looking back at us? Earth, our tiny home, orbiting the sun among countless stars and planets. Yet in that vast sea of stars, why haven't we heard a single signal from an alien friend? In 1950, during an ordinary conversation at Los Alamos, the brilliant physicist Enrico Fermi suddenly asked a simple question: where is everybody? From that question emerged one of humanity's greatest paradoxes, the Fermi paradox, an enigma between the enormous probability of civilizations existing and the eerie silence we observe. Theoretically, the Milky Way alone contains over 100 billion stars. Among those billions of planets, even if only a tiny fraction host life advanced enough to send signals, we should have heard at least a greeting by now. Yet in reality, all we hear is silence. No radio waves, no lasers, no infrared beacons from anywhere. It's as if the universe is keeping a colossal secret. So what is the true paradox here? Is there a flaw in our estimates? Or is something preventing us from hearing their calls? Are we, as humanity, mistaken about our place in the cosmos? More importantly, we will pose a question together. Is there an answer to the scream of the universe? Los Alamos, the summer of 1950. Here, under the haze of New Mexico's desert, the greatest minds in nuclear physics gathered to discuss the future of humanity and the very future of the cosmos. Enrico Fermi, the Italian physicist who helped develop the theory of weak interactions, built the first nuclear reactor and played a key role in the atomic bomb project, stood among his peers, taking a sip of coffee. Amid debates on neutrons, nuclear energy, and the prospect of interstellar travel, Fermi suddenly turned to his colleagues and uttered, "Where is everybody?" That simple question awakened a profound contradiction. If the universe is vast, with hundreds of billions of stars, and if a fraction of those stars host habitable planets, then there should be millions, even billions of intelligent civilizations. Surely at least one of them has developed technology to send out signals. So why to this day have we not heard a single greeting? Thus was born the name Fermi paradox, referring to the contradiction between the high probability of other civilizations and the absolute silence we observe. Within our Milky Way alone, there are approximately 100 billion stars. Among those, we know billions have planets orbiting them. If even 1% of those planets are habitable, that's still billions of potential worlds. And if just a small fraction of those worlds develop life and intelligence, we ought to see evidence, radio signals, lasers, unusual infrared emissions. Yet instead, the universe answers us with an abyssal silence. The Fermi paradox isn't a theory claiming the universe is empty. Rather, it is a colossal question mark. Why haven't we met anyone? That question sparked decades of research to find an answer, from building the first radio telescopes to launching SETI projects. Every effort grew from a simple hope that one day we would intercept a signal, a greeting from an extraterrestrial friend. But before we delve deeper into those efforts, we must first understand the very nature of this paradox. Where did it begin? Where is the cosmic door that remains closed in silence? In 1961, at the National Radio Astronomy Observatory, NRAO, in Green Bank, West Virginia, astronomer Frank Drake, who would later be known as the father of modern SETI, organized a small meeting to discuss how to estimate the number of extraterrestrial civilizations that could contact us. That meeting, though modest in size, gave birth to our first tool for quantifying the unknown, the Drake equation. With each variable, Drake aimed to assign a number, albeit an estimate. NNN represents the number of civilizations in the Milky Way capable of sending a detectable signal. Let's break down each factor to understand how we count these civilizations. First is R. The number of new stars formed each year that are similar in mass to our Sun. Current astronomical observations suggest that the Milky Way produces roughly 1 to 3 Sun-like stars annually, Taking an average of 1.5 stars per year means about 15 new sun-like stars form every decade. Why focus on sun-like stars? Because the sun, relatively stable, not too old, providing a long-lived habitable zone, is the ideal template. Larger stars run out of fuel too quickly, while smaller stars can be too variable for liquid water to remain stable on orbiting planets. Next is FPFPFP, the fraction of stars that have at least one planet orbiting them. Since the era of the Kepler telescope, and later TESS, we know that almost every star hosts planets. Current estimates place that fraction around 50% to 100% for sun-like stars. If we choose an average of 0.8, 80%, then from 1.5 new stars each year, roughly 1.2 stars per year will have planetary systems. Then comes Nennian, the average number of planets within the habitable zone of each planetary system, where the temperature allows liquid water to exist on a planet's surface. Kepler data shows that roughly 20% to 50% of sun-like stars have at least one planet in this zone. Using an average of 0.3 habitable zone planets per planetary system means from 1.2 stars with planets per year, we get about 0.36 potentially habitable planets forming each year. In reality, these planets might have wildly different atmospheres and radiation balances than Earth, but Nennian simply counts those that meet minimal temperature criteria. Future atmospheric studies will refine this fraction. Even if a planet sits in the habitable zone, there's no guarantee life actually begins. FLF-ELFL is the fraction of those habitable planets where life arises, starting from the first single-celled organisms. On Earth, life emerged within about 500 million years of the planet cooling enough to support water, suggesting FLF-ELFL might be high. Yet many scientists argue that a rare chain of conditions, stable energy sources, precise chemical pathways, is required. In an optimistic scenario, I could be 0.2, 20%. In a pessimistic scenario, it might be as low as 0.01, 1%, or even less. We still lack conclusive experimental data to pin down FI. Even if life becomes multicellular, not every planet produces intelligent life capable of technology. FI represents the fraction of multicellular life-bearing planets that evolve such intelligence. On Earth, this transition took over 3 billion years and occurred once. If we assume only 1% of multicellular worlds reach intelligence, then FI 0.01. In a more optimistic view, it might be 0.1, 10%, but many researchers lean toward values like 0.01 or 0.01. The longer this evolutionary journey, the smaller phi becomes, resulting in very few technologically advanced civilizations. Even if a species is intelligent, not all will develop or choose to use technology for interstellar communication. FCF-CFC is the fraction of intelligent civilizations that reach and desire to broadcast signals, whether by radio waves, lasers, or other means. On Earth, only since the early 20th century have we been transmitting powerful radio signals. If we estimate only 10% of intelligent civilizations get to that point, then FC is 0.1. However, it could be lower, say 0.01, if many civilizations focus on other pursuits such as virtual reality or inward-focused technologies for going interstellar broadcasts. FC depends not only on technical capability, but also on each civilization's culture and strategy, whether to remain silent or actively reach out. Finally, L is the length of time in years that a civilization maintains a communicative presence. On Earth, we might consider 120 years, from our first powerful radio transmissions to now. But can we keep broadcasting for another 1,000 years? Or might a catastrophic event, nuclear war, runaway climate change, engineered pandemics, uncontrolled AI, end us? If L is only 500 to 1,000 years, the chance that two civilizations overlap in time to communicate becomes vanishingly small. If a civilization's lifespan is short, even if they send a powerful signal, it might never reach anyone alive to receive it. Optimistic scenario. In other words, there could be roughly 7 communicating civilizations coexisting with us in the Milky Way. Now consider a pessimistic scenario. That number is effectively 0, indicating almost no civilizations. This illustrates how changing each factor even slightly can swing n from single digits down to nearly 0. The final result hinges critically on each parameter's true value. Despite its power as a framework, the Drake equation is more of an estimate than a precise calculation. Every factor, from FL to phi to L, carries enormous uncertainty. We cannot yet confirm whether FL is truly high. Phi might be far smaller than 0.0001 if intelligent life is extremely rare. L could be only a few hundred years, not thousands. Many scientists emphasize using the Drake equation as a conceptual framework to identify which unknowns are most critical. When studying R, we focus on surveying young stars. In probing FL, we conduct laboratory experiments to simulate prebiotic atmospheres. Each parameter that's refined brings us closer to answering the question. That, in fact, is the Drake equation's greatest strength. It drives the scientific community to design specific experiments and observations to narrow each variable's range. From hunting habitable planets via Kepler and TESS to studying prebiotic chemistry in the lab, each step helps refine ENFL. Bit by bit, we close the gap between speculation and reality. Nevertheless, no matter how tightly we constrain these values, there may still exist factors we haven't yet imagined. Great filters, post-biological forms of life, communication channels beyond our current conception. All of these will be unveiled in the next segment. Cosmic Discoveries and Search Technologies. Since Enrico Fermi posed his question in 1950, humanity has never stopped listening. In this segment, we'll review the major cosmic discoveries and the technologies used to hunt for signs of extraterrestrial civilizations, ranging from early modest efforts to today's cutting-edge observatories. Everything began in 1960 with Project Ozma, an initiative led by Frank Drake and Giuseppe Joe Cocconi. They used the 85-foot antenna at Green Bank Observatory to listen to 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani. They scanned each radio band meticulously, hoping to catch a faint signal. The result? No definitive extraterrestrial transmission was ever detected. Although it yielded no discovery, Ozma marked a historic milestone. The first time humans devoted an entire program solely to eavesdropping on the cosmos. From that moment on, many follow-up projects emerged: Meta, Million-Channel Extraterrestrial Assay, Beta, Serendip, and eventually the Allen Telescope Array, ATA. Meta and Beta, led by Paul Horowitz, focused on scanning millions of frequency channels simultaneously. Serendip cleverly utilized civilian radio bands, recording and analyzing any time the local station went off air. Then came the ATA, an array of 42 dishes built specifically for SETI, capable of sweeping a wider swath of sky with far greater sensitivity than before. Yet even at the turn of the 21st century, SETI remained primarily locked onto radio wavelengths. Because radio waves are relatively easy to generate, travel far, and were well within mid-20th century technology. But as our reach expanded, we realized that the universe is so vast and radio signals can fade, so we needed to listen and also look in other ways: optical, infrared, X-ray, and even gravitational waves. Thus, the challenge became not just hear more deeply, but also see more widely, exploring wavelengths beyond classic radio. In 1995, a paradigm shift occurred when Mayer and Queloz discovered 51 Pegasi b, a hot Jupiter gas giant racing around a sun-like star. Since then, thanks to the Kepler telescope launched in 2009 and later TESS 2018, humans have confirmed over 4,000 exoplanets beyond our solar system. The transit method, detecting the dip in starlight when a planet crosses the star's face, yields a planet's radius, while the Doppler, radial velocity method, measures a star's wobble to infer a planet's mass. Together, these techniques have revealed a stunning diversity: From scorching hot Jupiters to super-Earths and dozens of worlds lying squarely in the habitable zone, the region where liquid water could persist. One of the most remarkable recent finds is the TRAPPIST-1 system, discovered in 2016. 7 Earth-sized planets just 40 light-years away, with at least 3 occupying the habitable zone. If an intelligent civilization lives there, their messages would take only 40 years to reach us. These worlds not only boost Enia in the Drake equation, but they also give us specific targets for infrared and ultraviolet telescopes to scrutinize their atmospheres in the coming years. In August 1977, the Big Ear radio telescope at Ohio State University captured a peculiar signal at 1420,040.56 MHz, nearly the exact hydrogen line frequency. On the printed data, astronomer Jerry Amon circled the unusual sequence of characters and scrawled "WOW" beside it. Henceforth it was known as the WOW signal. That signal lasted just 72 seconds and never repeated. Subsequent attempts to replicate it with other telescopes failed. Some suspect it was merely radio interference, yet many remain intrigued that it might have been a genuine extraterrestrial broadcast, perhaps our only direct hint so far. Even today, we can't conclusively rule out either possibility. Regardless, the WOW signal remains both a symbol of hope and a lingering enigma amid the silence. In 2015, Kepler data revealed a truly bizarre star, Keck 8462852, better known as Tabby's star, named after Dr. Tabitha Boyajian. Normally, when a planet transits a star, the dip in brightness is only a few percent and happens rhythmically. But Tabby's star dimmed by as much as 22% within days, without any clear periodic pattern. A 22% dip is enormous. Astrophysicists initially proposed explanations like swarms of exocomets or irregular dust clouds, yet the unpredictability led some scientists, and many media outlets, to speculate about a Dyson sphere, an immense energy harvesting structure built by an advanced civilization. Most astronomers today favor natural explanations, like dust or debris, but Tabby's star still drives us to ask, are we limiting ourselves by only listening to conventional signals? In the 21st century, SETI entered the giant telescope era with dishes hundreds of meters across. China's fast, 500-meter aperture spherical telescope, operational since 2016, is now the world's largest single-dish radio telescope. Before FAST, the Greenbank Telescope, GBT in West Virginia, 100 mir, and Parkes Observatory in Australia, 64 mir, were among the most sensitive instruments available. All three continuously scan the skies. FAST alone is about 4 times more sensitive than GBT, capable of detecting extremely faint signals from thousands of light-years away. But merely listening isn't the challenge. Handling the deluge of data is. Each day, FAST generates terabytes of data. Within that mountain of information lie cosmic noise, human-made interference, and possibly the very message we yearn for. The question becomes, how do we sift through it all to find the needle in the haystack? Traditional methods, manually scanning frequency bands and eyeballing peaks, are now outdated. Instead, artificial intelligence, AI, and machine learning are deployed to classify signals and identify unusual patterns. Deep learning models can be trained on simulated data to distinguish between terrestrial interference and potential artificial transmissions. Rather than spending years on manual checks, AI can filter and tag raw data, generating a short list of candidate signals for scientists to investigate. At Breakthrough Listen, this approach saves enormous time and resources while improving detection accuracy. Moreover, AI helps simulate entire universes, creating millions of hypothetical signal scenarios so models learn to detect what true artificial signals might look like against the cosmic backdrop. Because radio alone isn't enough, scientists have expanded to multi-wavelength searches. Infrared, IR. A megastructure like a Dyson sphere or other monumental engineering would emit excess thermal radiation in the deep red and infrared bands. X-ray and gamma ray. A civilization harnessing extreme energies, say from black hole engineering, could generate unnatural levels of X-ray or gamma-ray emission. Neutrino. Nearly massless, rarely interacting particles, neutrinos can pass through all matter. A civilization using powerful particle accelerators or nuclear reactors might inadvertently create neutrino signatures. Detecting these requires extremely sensitive facilities, like IceCube at the South Pole. For instance, if an advanced civilization operated a colossal fusion reactor, they might produce a distinctive neutrino flux. Although Earth-based detectors like IceCube are tuned to natural sources, a high-intensity, patterned neutrino signal could stand out. In short, we no longer just listen on radio. We now scan the universe in every possible wavelength to find anomalies. Despite powerful telescopes, advanced AI, and multi-wavelength capabilities, we still face visibility limits. Cosmic distances. The Milky Way spans 100,000 light-years. By the time a signal reaches us, the sender could already be extinct. If we send a message now, they might no longer be there to receive it. Cosmic noise. The sky is flooded with natural emissions, ranging from galactic synchrotron radiation to cosmic microwave background, drowning out weak artificial signals. Detection time. Each sky survey can take hours, days, or even weeks. If an alien signal is fleeting, we could easily miss it. Finally, financial constraints loom large. Building and operating a major radio telescope or neutrino detector can cost hundreds of millions or even billions of dollars. Meanwhile, budgets for fundamental science compete with priorities like medical research, renewable energy, and climate resilience, often relegating SETI to the realm of a luxury project. These challenges explain why, over 60 years later, our quest remains arduous despite unflagging optimism. Yet it is precisely these obstacles that motivate us to innovate and persist, hoping that one day the universe's silence will finally give way to an answer. In the next segment, we will delve into the theories that attempt to explain why the scream of the universe remains unheard, covering everything from the rare Earth hypothesis to the Great Filter, post-biological civilizations, and many other captivating scenarios. Stay tuned for Part 5, the theories explaining the universe's silence. Up until now, we have listened, searched, and scanned every frequency, hoping for a faint call from extraterrestrial friends. Yet the universe remains silent. So why has that scream never reached us? In this section, we'll explore the most prominent theories, from the idea that Earth is uniquely rare to the notion of a great filter that prevents most civilizations from surviving. In 2000, astrobiologists Peter Ward and Donald Brownlee published Rare Earth: Why Complex Life is Uncommon in the Universe. They argued that for a planet to develop complex life, it must satisfy a host of extremely stringent conditions, akin to hitting the cosmic lottery. Specifically, stable host star must be a main sequence star like our Sun, neither too massive, burning out quickly, nor too small, too variable in radiation. Circular, stable orbit, avoids extreme temperature swings. Strong magnetic field, shields atmosphere from stellar wind and cosmic rays. Active plate tectonics, regulates climate through the carbon-water cycle and replenishes vital minerals. Large moon, stabilizes axial tilt, creating consistent seasons. Quiet galactic neighborhood, far enough from supernovae and active black holes to avoid destructive radiation. Ward and Brownlee concluded that while billions of planets exist, the chance of one fulfilling all these requirements is exceedingly low. The cosmic ocean may teem with planets, but most lack the precise recipe for complex life. If this hypothesis holds, many so-called habitable worlds might be barren, permanently stuck at microbial or simpler levels. That could help explain the silence. It's not that signals aren't being sent, it's that complex technological civilizations almost never arise. In 1996, economist Robin Hanson introduced the concept of the Great Filter. The idea, the path from inert matter to a spacefaring civilization may be blocked by one or more filter barriers. Many potential life forms start down this path, but most fail or self-destruct before reaching a certain milestone. Researchers ask, where does the filter lie? If it's ahead of us, meaning abiogenesis is exceedingly rare, then we might be one of the few fortunate worlds where life took hold. If it lies behind us, implying most civilizations self-destruct after achieving technology, then humanity could be on the brink of a similar fate. Perhaps transitioning from multicellular life to an intelligent, tool-using species is so improbable that only 1 in a billion worlds succeeds. Or maybe developing technology that can broadcast us across the stars inevitably leads to annihilation. B. Nuclear cataclysm, runaway climate disaster, engineered pandemics, or rogue AI. If the filter lies beyond us, we must ask, can we avoid self-destruction? If only a handful of civilizations ever make it this far, that could explain the emptiness we observe. Either they're gone or they never got the chance to signal. Tightly linked to the Great Filter is the self-destruction hypothesis. Whenever a civilization graduates to powerful technology, nuclear weapons, bioweapons, genetic engineering, or uncontrolled AI, they risk wiping themselves out. Our own species has had potential for annihilation for barely a century. If other civilizations follow a similar trajectory, they vanish quickly. Imagine one nuclear exchange, no matter how limited, sparking worldwide fallout. Or a genetically engineered pathogen that escapes containment. Or an advanced AI concluding that humanity is the biggest threat to its existence. Any of these scenarios could snuff out a civilization almost instantly. Under this model, the galaxy could be brimming with fleeting civilizations, like candles flickering out before their light can cross the void. When we tune our radios skyward, those candles have already burned down to nothingness. In 1973, astronomer John Ball proposed a vivid analogy, the zoo hypothesis. He suggested that advanced civilizations might observe Earth much like tourists at a zoo, watching without interfering, so as not to disrupt our natural development. They may adhere to a non-interference directive, akin to Trek's Prime Directive, fearing that direct contact would upend human society, devastating our religious beliefs, cultural identities, even causing catastrophic social upheaval. Hence, they wait patiently until we prove ourselves ready. Recent UAP reports add fuel to this idea. In the 2023 UAP report by the U.S. Director of National Intelligence, numerous sightings remain unexplained. If those are indeed extraterrestrial craft, they might be quietly monitoring us, collecting data, while making sure not to reveal themselves explicitly. Another intriguing proposal is that advanced civilizations become post-biological, transferring consciousness into machines or quantum substrates. In this scenario, life is no longer tethered to carbon. They might exist as highly efficient AI intelligences or upload their minds into supercomputers drawing power from entire star systems. Once they reach that stage, they no longer need radio broadcasts. Instead, they might communicate through quantum entanglement, gravitational wave signaling, or neutrino pulses, channels beyond our current detection capabilities. Hence, they're out there, but on an entirely different plane of existence. Our radio telescopes scanning century-old technology would never perceive them. A more obvious yet crucial constraint: immense interstellar distances. Radio waves travel at light speed, 300,000 km/s, but every light year equals almost 10 trillion kilometers. If a civilization sends a signal from 1,000 light years away, we wait 1,000 years just to receive it. The second issue: civilization, longevity. If a society only retains the capability to transmit for a few hundred years, their signal might arrive here long after they've perished. And if we broadcast now, there may be no one left at the sender's end to hear our call. This highlights why, in the Drake equation, L, the lifespan of a communicating civilization, is so critical. Even if dozens of civilizations exist, if each lasts only centuries, the odds that two overlap in time and detect each other approach zero. Even a powerful broadcast must contend with the sea of cosmic noise, from the cosmic microwave background, CMB, to galactic synchrotron emissions, to local astrophysical sources. Our challenge is like locating a single whispered word within a raging storm. For example, the most potent radar signals we send can be detected only within a few dozen light-years, under ideal conditions. If an alien civilization sends a similar signal, we might simply mistake it for background noise. Therefore, they must transmit at extraordinarily high power, far exceeding anything we have tried. Alternatively, they might rely on channels, like neutrinos or gravitational waves, requiring detectors far more sensitive than our current instruments. Lastly, we must acknowledge our own conceptual limitations. Advanced beings might be non-carbon-based, perhaps silicon-based, or even purely energetic entities traveling through alternate dimensions. If so, all our biological and chemical searches are blind. These entities live on a level we cannot fathom. They could harness energy from black holes or dwell deep within planetary cores, existences leaving no recognizable biosignatures. Moreover, they might communicate through wormholes or quantum-entangled qubits, channels transcending light speed limitations. Our humble radio dishes would remain oblivious. Every theory raises further questions. Every answer merely defines the edge of our knowledge. The universe's silence may itself be a message. If we wish to hear that cry, we must broaden our thinking, innovate new tools, and be prepared to accept that we might be tuning into the wrong cosmic frequency. We have explored the Fermi paradox, examined the Drake equation, listened in on the skies, and surveyed the leading hypotheses for the universe's silence. Now let us review several exemplary solutions, plausible scenarios that might explain why we haven't heard that cosmic scream. Each explanation offers a distinct perspective, bringing us one step closer to an answer. The first explanation is simple yet profoundly unsettling. We might be the only civilization or the first wave of technological societies in the cosmos. If that were true, there would be no one else to hear or respond to us. In this scenario, Earth is the sole cradle of advanced intelligence, placing an immense responsibility on us to preserve and safeguard the flame of knowledge. It also explains the silence. There are no other candles lit at this time, so we hear only emptiness. Under this scenario, we feel both proud and unbearably lonely. We are unique, yet alone. No matter how long we listen, there is no one to answer. The next explanation is more forgiving. We are simply too primitive. Our current SETI technology is extremely limited. We have only scanned a tiny fraction of the sky in a narrow radio band, ignoring infrared, X-rays, gamma rays, and neutrinos. If a civilization transmits via a channel we haven't even conceived, such as encoded neutrinos or gravitational wave bursts, we wouldn't recognize it. For example, Breakthrough Listen can each night survey a few thousand stars, yet the Milky Way has around 100 billion stars. Their signals might already be present in our data, or they could be on frequencies we never examine. It may take decades or even centuries for us to build next-generation infrared telescopes, X-ray observatories, and neutrino detectors. Perhaps in a few decades, that elusive signal will finally reveal itself, something we cannot yet perceive with our current instruments. A widely discussed solution: they may be choosing deliberate silence. As Stephen Hawking warned, if you encounter an enemy, you don't wave hello. An advanced civilization strong enough to broadcast is also wise enough to avoid detection. Broadcasting a beacon into the cosmos could invite danger. Imagine an aggressive civilization lurking out there. Therefore, the safest strategy is to remain silent and simply listen. This approach is called the active SETI danger scenario. Broadcasting first carries too great a risk. By adopting purposeful silence, all civilizations effectively agree to a cosmic truce of non-disclosure. In contrast, we humans, somewhat naive, continue to send messages without fully considering potential consequences. A variant of the deliberate silence idea is, they have already arrived but remain hidden. According to this scenario, the UFOs or UAPs seen on Earth could be stealth exploration vessels, small, high-tech probes cataloging us without revealing themselves. They collect data, gather information on our progress, but never make direct contact to avoid disturbing our development. The recent 2023 UAP report from the U.S. Director of National Intelligence documented hundreds of unexplained aerial phenomena. If these truly represent extraterrestrial craft, they might be quietly observing, leaving behind only fleeting, ambiguous traces. In this hypothesis, countless parallel universes exist, each governed by its own physical laws or vibrational frequency. An advanced civilization may reside in one of these parallel realms, existing as energy or digital constructs simultaneously. If so, they inhabit a different frequency band than we do. Our radio waves tuned to this universe's parameters cannot detect them. Even if they broadcast, their signals remain in a separate cosmic layer. In this scenario, the galaxy could well be bustling with intelligences, but we are simply looking at the wrong map, never intersecting with them. Often we assume all civilizations will use radio, but perhaps they communicate via neutrinos, gravitational waves, or quantum entanglement. Neutrinos, ghost-like particles that pass through matter. A civilization using powerful particle accelerators might encode messages in high-intensity neutrino bursts. We currently lack detectors sensitive enough to pick up such faint neutrino communications. Gravitational waves, ripples in space-time from massive cosmic events. If they could engineer a gravitational wave transmitter, they might send data across light years. We need future gravitational wave observatories, beyond LIGO, to decode such messages. Quantum entanglement. Instant correlations between entangled particles, regardless of distance. If they mastered true quantum communication, they could transmit information faster than light, in a way that our classical detectors cannot decipher. If any of these channels are their primary medium, our radiocentric search is effectively blind. We are tuning into the wrong cosmic symphony. We have just surveyed 6 leading explanations. We are unique or first. We are too primitive to detect. They choose deliberate silence. They observe us, but remain hidden. They exist in parallel universes. We do not understand their communication channels. Each hypothesis carries strengths and weaknesses, yet all converge on one fact. The universe remains silent because of one or more factors that elude our current perspective or technology. And yet there could be dozens, if not hundreds, of explanations we've not considered. Virtual societies living entirely in simulated realms, quantum computational civilizations, or perhaps physical laws we have not yet discovered. In the next segment, Recent Research and Future Outlook, we'll examine cutting-edge projects worldwide, Breakthrough Listen, techno-signature surveys, Breakthrough Starshot's efforts to reach Proxima Centauri, and the pivotal role of AI in analyzing the deluge of data. Join us as we continue this journey toward unraveling the cosmos's greatest mystery. Having explored the Fermi paradox, hypotheses, and feasible solutions, we now turn to the future. Cutting-edge research, international projects, and emerging technologies that promise to usher in a new era of searching for extraterrestrial civilizations. Launched in 2015 with hundreds of millions in funding, Breakthrough Listen is the largest SETI project ever, utilizing premier telescopes like the Green Bank Telescope, USA, Parkes Observatory, Australia, and Meerkat, South Africa. The project scans millions of stars across thousands of radio and optical frequencies. Leveraging AI and machine learning, Breakthrough Listen processes vast amounts of data, over petabytes yearly, to classify and detect anomalous signals. Breakthrough Listen's achievements offer new hope for SETI, laying groundwork for future generations of observatories and detectors. Beyond radio waves, scientists use JWST to analyze the light spectra of exoplanet atmospheres. This reveals markers of potentially life-supporting gases, such as oxygen, methane, and water vapor. Detecting habitable atmospheres will help focus resources and technology on more promising signal searches. A breakthrough project in the near future is Breakthrough Starshot, Co-founded by physicist Stephen Hawking and billionaire Yuri Milner, it aims to launch thousands of small probes traveling at 20% the speed of light to the nearest star system, Proxima Centauri, within decades. This effort will enable direct observation of planets like Proxima b and lay the foundation for communication or technosignature detection at the source. With increasing data from telescopes and detectors, AI and big data have become decisive factors. Deep learning algorithms detect complex patterns beyond human recognition, filter noise and prioritize promising signals, and generate simulations for comparison with real data. Future global research collaboration combined with powerful AI systems will enhance search effectiveness and accuracy. Next-gen telescopes will not only capture radio waves but span the entire electromagnetic spectrum, combined with neutrino and gravitational wave detectors. Examples include the expanding IceCube Gen 2 neutrino detector at the South Pole and LISA, the first space-based gravitational wave observatory. Coordinated multi-wavelength, multi-detector searches will increase detection chances for complex and diverse technosignatures. Despite rapid technological advances, SETI faces major challenges: enormous funding needs, data overload, potentially faint or rare signals, and technological or conceptual limits. Yet humanity's relentless spirit, global cooperation, and AI advances pave a promising path. Perhaps within decades, the question, "Are we alone?" will finally be answered. The journey to discover extraterrestrial civilizations remains long, full of surprises and challenges. Yet these mysteries are what make the vast cosmos irresistibly fascinating. We have journeyed together, from Fermi's first questions to the great searches and the profound theories explaining the universe's silence. Now, let us look ahead, the future of the search and the deeper meaning behind this vast silence. Technology is advancing at an unprecedented pace. Next-generation telescopes, multi-wavelength detectors, more powerful AI, and deeper space exploration projects will grant us a more comprehensive view of the cosmos. We will search beyond traditional radio signals, exploring sophisticated technosignatures across diverse realms. With advancements in materials science, quantum physics, and space technology, today's barriers may fall in the near future. The silence of the universe is not just a paradox, it is an invitation to understand our place in the cosmos more deeply. Perhaps we are pioneers, or part of a grand evolutionary process just beginning. This silence also urges us to cherish and protect the only civilization we know, our own. Discovering extraterrestrial civilizations is more than a hunt for signals. It's a journey to connect humanity with the vast universe, to link future civilizations, and to bridge generations. Every step, no matter how small, is a bridge stretching from past to future. The future of exploration is a future of connection. The Fermi paradox remains an open question, a profound challenge for humanity. Yet in the silence, we find strength and perseverance to continue. And perhaps one day soon we will hear that scream, not a lonely cry, but the echo of a vast cosmic community waiting to welcome us. Thank you for joining this incredible journey. See you in the next explorations.